When did your softball season start?
We started practice right when we got back to campus, but we start on March 5th. Games.
Okay. So hopefully the snow will be gone then.
Yeah, I hope it's at least 40 degrees.
Yeah. How about soccer?
We just got a couple games added to the schedule, so our first game will be March 3rd.
Okay, so you're about the same timeline.
Yeah.
Okay.
I don't like the cold. I'm so used to starting the season off it being in the 90s.
Because it's usually in the fall, right?
Yeah.
Softball's always in the spring, is that right? Or is that?
At the college level, yes, but I played fall softball in high school,
Oh, okay.
so.
Well, at least it's better than last year, right?
Yeah.
Yeah.
Okay, we'll go ahead and get started. Can the people on Zoom hear me okay and see the slide? Yes? No? Can the people on Zoom hear me?
Yes, we can.
Okay, thanks. And you can see the slide as well?
Yes.
Thanks. Touch and go there for a second. Okay, so hopefully everyone survived the snow and ice and cold temperatures and that, and we're kind of moving past that now. So what we'll do today is we'll finish up chapter 14, the rest of the kinetic stuff. And then just want to remind you that on Tuesday of next week, so next class, that'll be an exam, cover chapters 13 and 14. So no need to come to class on that day, just go into Canvas during the class time and take the exam during the scheduled class period. So any questions about the exam or anything like that? Okay. All right, so last time we met, we started talking about factors that affect the reaction rate. And the four factors that we have a concern about when we talk about reaction rates are temperature, frequency of collisions, and if you think about that, those two are related. If you heat up the temperature, things start moving around faster and you get a better chance of collisions. And then another one is orientation of molecules. So in order for molecules to react, they have to collide, but they don't just collide, they have to collide in the right spots. So you think about it, when you do a reaction, you're breaking bonds and forming bonds. So you got to break the correct bonds, you got to form the correct bonds, or else the reaction doesn't go the way you want it to. And then finally, there's a certain amount of energy that needs to take place for that to be there for the reaction to take place. That term that we use to describe that energy that's needed for the reaction to go is called the activation energy. And so we'll talk about that a little bit too. When we think of temperature, in general, you increase the temperature, you increase the rate. And the rule of thumb is that for every 10 degrees Celsius temperature increase you double the reaction rate. And the other thing is that, remember we talk about a reaction rate constant. that value is temperature dependent. So usually when we think of constants, they don't change. Reaction rate constants do change. So whenever you see a reaction rate constant given, they should have on there what the temperature of that rate constant is for. So the one comment I'll make is, so, you know, if you increase the temperature by 10 C, then we're saying that usually you double the reaction rate, but you can't just keep increasing. Okay, there are some limitations there. One would be maybe you have a liquid and you keep increasing the temperature, you might start boiling the liquid, so you have a phase change, and that could impact it. Some compounds start to thermally degrade as you increase the temperature, so you wouldn't want to do that to the point of where you're degrading one of your reactants. So while temperature is a nice tool to increase the reaction rate, it's not, you can't just do it blindly. You got to think about some of this stuff. The other thing I would say about that is there are just some practical considerations of it, is that if you increase the temperature, it increases the reaction that you want. But in the equipment you're using, if you have, say, some kind of seal on there, plastic seal, it might increase the degradation of that, because that reaction is going to increase as well. So in general, reaction rates go up when you increase the temperature. That's a common way to get it to increase, but there are some limitations on what you can do. When we talk about the frequency of collisions, and so that collision stuff is based on the kinetic molecular theory, and it's based on the fact that for things to react, they have to come in contact with each other. And the more contact that you have, it just increases the odds of something happening. You know, it's like a lot of things in life. The more opportunities you have to do something, the greater the chance that one of them is going to work out. And so, and that's one reason why we have a bunch of quizzes and tests in here. We just have one quick test at the end. The odds of you getting a really good grade aren't as good as if you've got multiple attempts, you can drop a test and all that kind of stuff. So it's the same in collisions pertaining to reactions. And remember, as I said, when we talk about chemical reactions, bonds have to be broken and new bonds have to be formed. And so that can only happen if you have things colliding. But it can't just be any collision, okay? So there is an orientation component to it. Because when we're doing the reactions, we're not just trying to break any bond, for instance. There's a particular bond we're trying to make, and then a particular bond we're trying to form. So we have to have things lined up correctly as well. And so down here, in the pictures below at the bottom of the slide, we see first two molecules before the collision, then they collide. The collision happened at the right spot, and the energy was okay as well. And so then we form two new molecules. The second set of pictures, we have a collision again, but this time the collision happens at points where probably the energy isn't right, and so we don't get any reaction. They collide, they bounce off each other, and they go on their merry way. So you have to have the collision first of all, and we do things with temperature and other things to kind of increase the odds of that collision happening. And the nice thing about increasing the number of collisions, it increases the odds that you're going to get the right collision as well. And so by getting the correct collision and having the correct energy there, then you get the reaction occurring. So I mentioned that it has to have the correct energy as well involved. If you don't have enough energy, then the reaction doesn't occur. And so that energy, that amount of energy that's needed for the reaction to take place, we call that the activation energy. And the little cartoon down below with the golfer hitting the golf ball, and the golfer is trying to hit the ball hard enough so that it goes over that that hill, and then is able to go over the hill and go down to where the pin is. And so that kind of getting over the mountain type thing is a common way that people will describe the activation energy. And so you got to be putting energy into the molecule in the system so that it has enough energy to get over that hump, the energy hump in this case, and then the reaction can occur. And so just as with the golfer here, if the golfer doesn't hit it hard enough, it doesn't happen, it rolls back down. With the molecules, if you don't put enough energy in, you may have the right collision in terms of orientation, but if there's not the right amount of energy involved, the reaction doesn't occur. So the key things for a reaction occurring are you have to have a collision. That collision has to have the right orientation, and the right amount of energy has to be involved. So if you have all those things, then you'll have a successful reaction. Now, the other thing I'll say is that if you think about it, someone who's trying to get reactions to work or to prevent a reaction, these are the tools that the variables you would try and have tools to impact. You'd want to increase the collisions, and we talked about temperatures, a good way to do that. The orientation, well, it's kind of hard to orient the molecules properly, but one thing you can do is you can increase the number of interactions, and that increases the odds there. And with the molecules, there are some things you can do with solvents in that, but we're not going to get into that in this class. And then the activation energy, there's something called a catalyst that you can use, which impacts that. And we'll talk about the catalyst a little bit today. Okay, so when we're doing this reaction, the reactants gain the energy as a reaction, as you're doing the reaction, until they reach that maximum energy state, that activation energy. And the way the atoms are organized, and we'll see in a moment what that picture means, what organization means. That's called how they're organized at the higher energy state is called the transition state, or it's also called an activated complex. So, and as I said before, the energy at that let state is the activation energy. The other thing I'll mention is activation energy varies from reaction to reaction. Some reactions have low activation energies, some have high. The ones with low activation energies, those are going to proceed more easily than the ones with high activation energies. So when we think of the reaction, we have here kind of an energy diagram and reaction process. And so we start out with our molecule, energy is being added, we're going up, we're trying to get to the apex of this curve, because that's our activation energy. That's the level of energy we have to get to make the reaction occur. And then, but what you see is that as you add energy, then you start to get to where you can break bonds that you're interested in breaking. And so at the apex of this, you get the activated complex forms. And in this example, the activated complex is CH3 with this dotted line between the carbon and the triple bond and the CN triple bond. So that kind of temporary type of arrangement is what we mean by the organization of the molecule. And then it forms back to whatever it's going to be. And so in this case, we see that now we have a carbon-carbon bond, whereas before we had a carbon-nitrogen bond. So we broke that carbon-nitrogen bond. We had this activated complex up on the top at that activation energy peak. And then when it reformed, now instead of the carbon, the CH3 carbon, bonded to nitrogen. Now it's bonded to the carbon atom, and the carbon's still triple bonded to the nitrogen. And then we get our final product down here. Okay? And so we also see that our energy started out, we don't have that absolute number, but we see our energy started out relatively higher than what this final is. So that tells us that that's an exotherm. Okay, so it's a negative energy value. Remember, negative is exo. Okay. When we think of gas molecules, we usually talk about them with regards to an average temperature. Okay, so the gas has an average temperature, but really each of those molecules is going to have their own individual energy, so their own individual value of energy based on that temperature. And what we want is we want molecules that are higher in energy than the activation energy. That activation energy are higher, so the reaction occurs. And so in this plot that we have here, the curve that's in black is a lower temperature average value, and then the red one is a higher temperature value. And what we see is that we see the kinetic energy distribution at those two temperatures. And what we see is that the average kinetic energy is a little bit higher for the higher temperature one, which is what we would expect. We put more energy into it. But really the key thing here is we look at our minimum energy for the reaction. Once again, that's the activation energy. And we see not only did we get a shift of the average kinetic energy for all those gas molecules, but more importantly, if we look at the area under the curve that's greater than the activation energy, we see we have more molecules at that higher temperature that are above the activation energy than the molecules that are at the lower temperature. And so that means we've got more molecules that have the right amount of energy. So once again, it's going to increase our chances for that reaction to occur. So let's talk a little bit about the relationship between activation energy and temperature. So a guy named Arrhenius noted that there was a relationship between temperature and activation energy, and came up with this expression. Reaction rate constant equals A, which is another constant. We're not going to worry about that for now. E is, that's the natural log E, okay? So instead of being base 10, it's base E. And then EA is the activation energy. R is the gas constant, which we've used before, and temperature is expressed in Kelvin. And so this relationship between activation energy and temperature, this is a real famous relationship. This is one that's used all the time, and I'll explain to you in a moment why it's used so much. If you think back to when we were talking about orders of reactions, we did some rearrangement of formulas so that we could get to the point of where we could do a pretty simple linear plot and get some information about things. But we're going to do the same, we want to do the same thing here. And so if we take this Arrhenius equation here and do some manipulation to it, and for now, we're not going to worry about the steps in that. We're just going to get to the final products here. We see that we can say that natural log of K equals minus activation energy over RT plus the natural log of that A constant. So hopefully that arrangement looks familiar. This is that y equals mx plus b linear type of line equation arrangement. So the y variable would be natural log of k. The slope would be minus EA over R. And then on the x-axis, we would plot 1 over t. So if we plotted 1 over t on the x-axis and natural log of k on the y-axis, we should get a straight line. And that straight line should have a slope of minus EA over R. And then natural log of A would just be the y-intercept. And sure enough, if we do that, that's what we get. So here's our 1 over t, and t is expressed in Kelvin on the x-axis. The y-axis is natural log of k, natural log of that rate constant. And we see we get a straight line, and we see the slope of that line is minus EA over R. The reason why this is so convenient is by plotting this data, we can easily then calculate out what the activation energy is for whatever this reaction was. Because R is a constant, we know that, so we could plug that in, and then we could just solve for EA. The other thing that this equation can do is, once again, you can do some more manipulation of it. And when you go and do it for 2 temperatures, okay, the math works out that the A term drops out. So that's what I'm saying, we're not going to worry about this. And this form of the equation, this natural log of K1 divided by K2 equals activation energy divided by the gas constant, and then that times 1 over T2 minus 1 over T1. This formula here, I guarantee you will have to use that on the exam on Tuesday, okay? So we have some homework problems, and we'll go through some here in class, but make sure you know how to use that formula, all right? And so what's important about this is it allows us to calculate out rate constants or activation energies for when we have 2 different temperatures involved, to see that difference. This equation, to kind of see what happens to rates and things like that at 2 different temperatures, is used all the time in the pharmaceutical industry to determine if a new active ingredient is stable or not, and predict stability. And so what you'll do is you'll take that material and you'll put it up in a stability chamber at a couple different temperatures. Usually it's like 40 degrees, or maybe 40 and 60, or 40 and 30 C. And then you'll analyze it over a period of time, get some of that concentration data, and then you'll use this equation to give you a feel for what the rate is and what that rate constant is. And the reason why that's important is, if you want to know if something's thermally stable, you can set it at, say, 30 degrees C and let it sit for 2 years. But how long does that take? 2 years. You don't want to wait 2 years and then find out it fell apart. You would rather do some higher temperatures, get some of that rate information, and know this is stable or it's not stable. So this Arrhenius equation, especially in this last form here with the 2 temperatures, really an important equation in understanding how materials, how molecules hold up at various temperatures, and giving you a feel for, okay, do I need to store this below a certain temperature or not, or things like that. The other thing I'll mention is, if you notice in these equations, we're using ln(k). Okay, ln is the natural log. Previously, I think we've always used the base 10 log. So what that means is, on most calculators, at least I know it is on mine, you have an log button to find the base 10 log, and then you have an ln button to find the natural log. Make sure you know how to do that on your calculator, all right? Your calculator may be different, it may not be termed that way on the keys, but make sure you know which keys are associated with the natural log. And then if you need to find the anti-log, for the base 10, we would use that 10, on mine, I would use the 10 to the X key to find the anti-log. For natural log, it's the E to the A key on a lot of them. And that's how you find the anti-log there. So make sure yours might be different. So that's why you want to make sure you do a few of these homework problems so you're comfortable with doing the calculations. Okay, so we talk about the kinetics and we have a rate law, but the reality is that most reactions don't really occur the way we write them. So we write a couple of reactants and then we get a couple of products. So that part's correct. It's just the path usually isn't that direct. Usually it goes through some other compounds before we get to those products that we have listed. And those products and those stepwise fashion to get from reactants to final products, we call that process a reaction mechanism. And so there's these intermediate steps in there that make up the mechanism. And so we're going to talk about that a little bit. Of what we mean when we talk about steps in the mechanism. So there's a term called molecularity, and so in this table it kind of walks us through what we mean by that. So if we say something is unimolecular, then it's one thing and it goes to products. A lot of times that unimolecular reaction is just a degradation reaction, okay? Then we have bimolecular. We have two examples of that. So one could be two of the same molecules reacting together to form some product. And then the other version would be two different molecules reacting together to form a product. For these two examples, the unimolecular and the bimolecular, we have rate laws over here. So the rate law for unimolecular is K times A. The rate for first bimolecular is K times A squared. And the third is K times A times B, those concentrations. There's also something else called termolecular, and that's where you have three things. And it could be three of the same, it could be two of the same, and then another different one, or it could be three different ones. And then we have rate equations over here on the right expressing how those would be. The reality is these termolecular ones really don't happen very often. So we're not going to worry about these too much. If you're trying to work out a mechanism and it's based on a termolecular step, you might want to go back and reevaluate your mechanism, because usually that's not what's happening. It's not impossible, it does happen sometimes, but that usually isn't the case. And so if you're trying to figure that out and you come to this conclusion, yeah, I don't know, probably isn't correct. Why do you think it's difficult for these termolecular things to happen, these reactions to happen? Any thoughts on that? Well, what did we say we needed to have to get a reaction to occur? We said they had to collide, right? What else?
Is the orientation, right?
You got orientation, that's important, yeah. And so if I ask the people in the class to run into each other right now and run into each other a certain way, it would be hard to do, right? If I took three of you and had to ask you to do that, the odds of it is one of you is going to be turned the wrong way or not run fast enough or something like that, because it's just harder to get three things to collide that certain way than it is two. That's really one of the big reasons, is now you have three things that have to have the right energy, the right orientation, they have to collide at the same time. It's just an odds thing in my mind. So What this molecularity does tell us, though, is it tells us how many molecules are involved. And like I said, usually it's one or two, and even with the one or two, it's usually two. It's usually two things reacting together. The one tends to be the decomposition reactions, which can occur, but okay, here this is just talking about how the term molecular doesn't happen very often. If it does happen, it's usually pretty slow. And once again, it's just, you got to line all this stuff up, and it just takes more time and it's less likely to happen. So if we're saying that a lot of these reactions don't just go from reactants to products that way we write our balanced equation, that there's some intermediate steps in there. Then when we're trying to figure out how long it takes for the reaction to occur, one of those intermediate steps is going to be what we call the rate determining step. And so they usually all those intermediate reactions don't occur at the same pace. And so one of them is usually slower. And that slowest one is the one that really determines the overall rate. So, because if you speed up the others, but you still have that slow one in there, well, it doesn't really matter that you speeded up the slow ones that much. So one of the things that people who study this kind of stuff are really interested in is figuring out which step in the mechanism is the rate determining one, so that then they can do some things to try and speed up that step and thus speed up the overall reaction. Let me ask you this question. Why do you care if the reaction is fast or not? What difference does it make? Any guesses on that? Anybody on Zoom have a guess on why you like to speed up reactions? It's faster, you can make more of it, cost you less money, things like that. Think of it this way. Think of it if instead of us just having an hour and 20 minutes reserved for this class, we said, okay, instead of that, I'm going to present 20 slides and then we're going home. Would you want me to go faster or slower? You want me to go faster? Yeah, I think we all can agree on that. Because then instead of being here now 20 minutes, maybe we only be here for 20 minutes or something like that. And it's the same with reactions. You like to speed them up as long as you're still making the same stuff. You don't want to mess up the chemistry, but doing it faster has advantages. You can run the reactions more frequently, so that's less time sitting in the lab, or make more batches if it's in a production environment. So that's why people like to understand the reaction times and speed them up. So a couple things here when we talk about these mechanisms is that the stoichiometry of the steps, when you add up those steps, it has to equal the stoichiometry of the reaction, okay? So your individual steps can't wind up with being something that doesn't give you what you had as reactants or doesn't give you something that you didn't have as products. Each of those steps also has to be balanced. In other words, you can't have unbalanced intermediate reactions. Any intermediates that you form, and we'll have some examples of this in a little bit, intermediates that you form, that you make them and then you use them up. And that just means those intermediates can't show up in that final balanced reaction. And then finally, if you are using a catalyst, the catalyst participates in the reaction, but it can't show up in the products, the molecules. So if you have, for instance, some platinum you're using as a catalyst, none of those product compounds can be platinum containing. Okay, so let's take a look at a reaction, and we're told that this reaction has its initial step is slow. Okay, so we're told that the reaction is, the overall equation for the reaction is NO2 plus CO going to NO and CO2. And we're told that experimentally the rate was determined to be rate equals the constant times NO2 squared. So we're told that this has a slow initial step. If that initial step is slow, then that tells us that first step is the rate determining step, right? Because we said whichever one of the individual reactions is the slowest is the rate determining. And so what that means is the coefficients on the reactant side are going to be the same as the order of the rate law. And what order is that rate law? Anybody remember? I see a 2, that's right. It's a 2 because even though we only have one concentration, it's squared. So that tells us it tells us the order of the rate, but it's the second order. And so what that means is we need to have 2 of these NO2s, right? So the first step begins with NO2 plus NO2. We're told that the easiest way to complete this reaction is to make NO plus NO3. And let me just tell you this right now is, we're going through a couple examples of reaction mechanisms. We're not learning reaction mechanisms in Gen Chem. Okay, you'll learn that if you take organic or some other classes later on. We're using these as examples to show you what we mean by these mechanistic steps involved in reactions. So you're not going to get tested on reaction mechanisms, let me just tell you that. So now what we see here is we see NO2 plus NO2 forming NO plus NO3. When we go back and remember what our reaction stoichiometry was, that's that first equation, which is labeled overall equation. We see we have NO2 plus CO going to NO plus CO2. We don't see the NO3 in there at all. So what that means is that NO3 must be an intermediate, because remember we defined an intermediate as something that shows up in one of the steps, but doesn't show up in our final equation. So since it's an intermediate, it tells us it's going to be used up in the next step. And here's that next step, NO3 plus CO going to NO2 plus CO2. Well, the top equation is what we said was our overall equation for the reaction. That was the NO2 plus CO going to NO plus CO2. Based on the information we were given, we were able to figure out that NO2 plus NO2 going to NO plus NO3 is the first step in our mechanism. Then our next step in the mechanism was using up this NO3, and so that reacted with CO to give us NO2 and CO2. If we combine these two intermediate equations, I have the NO3s highlighted in yellow. That's because if I have one on the reactant side and one on the product side, that cancels out, right? And that further reinforces that NO3 is an intermediate, because it was formed, but then it's used up, so it doesn't show up in my final balanced equation. If I look at the NO2s, I have an NO2 here in the first equation on the reactant side, and I have an NO2 in the second equation on the product side, so those are the two in red. So those can cancel out as well, right? So that leaves me with an NO2 and then going to NO from the first equation, and CO going to CO2 in the second. We combine those, and we get NO2 plus CO going to NO plus CO2. That matches what we said was the overall reaction equation. So this is an example of what we're talking about with these mechanisms. We write our equation for what's going on, and that's the NO2 plus CO going to NO plus CO2. But as I said before, it's not that simple. It's not just NO2 reacting with CO, and then we get this other. It's actually these two steps occurring. The NO2 plus NO2 reaction, and then the NO3 plus CO reaction, and it involves the intermediate of NO3. So this is usually what happens in reactions, is you write it such that you have your reactants and your products, kind of what you started with, and then what you wind up with. But actually, in terms of what happens to get from that start to finish, usually has these intermediate steps in here. And sometimes you want to isolate the intermediate and do something with that for various reasons. Sometimes you don't isolate it, you just let it go. It can be either way. And there's a lot of factors that go into that. Any questions about this? Okay. This is just saying what we were talking about. If you add them up, the individual steps, you should get that overall. Each step should balance. Our steps balanced. The total thing makes sense. So this is a reasonable explanation for the mechanism. So just talking about the intermediates for a little bit is the intermediates aren't the reactants and they're not the products. There's something that forms in between. We talked about how as we get to the top of the activation energy, the molecules are kind of getting into a configuration that they can react. That's a transition state. So that's not the same thing as an intermediate. Intermediate is you actually form something, okay? And if you stop the reaction right there and analyze the solution or whatever it is matrix you're in, you would be able to find that compound there, okay? That's what the intermediate, and on these energy diagrams here, where we have reaction progress on the x-axis and potential energy on the y-axis, what you'll see is this increase in potential energy, so you get the transition state. You get to that point, the reaction starts to occur, and then you made whatever the intermediate is, and that you always have a dip there in this plot. And that's where the intermediate is. Then that intermediate has some kind of activation energy associated with it to get to its transition state and then react to form whatever is next. So, like I said, intermediates are stable. And when we say stable, what we're usually talking about is you could, if you really wanted to, you could isolate it and analyze for it and things like that.
I have a question.
Yeah.
Could there be multiple intermediates, meaning more than two transition states, or is it just the one?
So you're just going to have one transition state and then have something form on that. And then you'd have another one like on this. So this wouldn't have to go to products. This could go to another transition. This could go to another intermediate. You could have another and you could have another.
Yeah, that's what I'm asking.
Yeah, that gets to where how many steps in the reaction. We're doing kind of a simplified version of where there's just, in this case, two steps, but you can have a whole bunch of steps in the reaction.
All right, that was my question.
Yeah. You gotta take organic chemistry to get that fun. So,
No, thank you.
some people love it, some people hate it. I was not one who loved it. Okay, let's look at another example. And this time, remember the last one we said the first step was slow. We were given that information. Now we're being told that the first step is fast. So that means that first step's not going to be the rate limiting. And the equation for this reaction, we're told, is 2NO plus Br2 going to 2NOBr. And we're told that experimentally, the rate law was determined to be rate equals rate constant times NO squared times BR2. Wait a second, I think we got a term molecular process, right? We got 2 of this and 1 of that, it's 3. And I told you that doesn't happen very often. Well, I didn't lie. What it means is we're gonna assume something else is going on, that this is a multi-step reaction, because of the fact that those term molecular things don't happen very often. So if you happen to have a term molecular thing, you want to check out the other options before you go down that path. So even though the rate law suggests that, we're not going to be fooled by that, because we know that that's the sum of all the steps. Okay, so we were told that that first step was fast, and so that means the second step is slower. And so if we go and look and say the first step is NO plus Br2, we form NOBr2. Then the second step is NOBr2 plus NO forming 2NOBr. There's a couple of things I want to point out here is, first of all, don't worry about how did we figure out this is what the reaction is. That's not the point of the exercise. The point of the exercise is 2 things. Notice on this first step, we have double arrows between the reactants and products. And double arrows, as you may remember, signifies equilibrium. So it means it's going back and forth, all right? So the NOBr is reacting to form, Br2 is reacting to form NOBr2, Br2 is going back the other way at some equilibrium. In the meantime, NOBr2 that's formed here, so NOBr2 would be called what? Be called the intermediate, right? Because now it's going to react with NO down here in step 2, and we see that arrow just goes one way, so that's not an equilibrium reaction. That's just simply NOBr2 reacting with NO to give us NOBr. So what's going to happen is we have this equilibrium going on in step 1. As we produce NOBr2, then it's going to react with NO down here and form the NOBr. Each of these reactions individually are balanced. And if we go and then we add these 2 steps together, what do we see? We see on the reactant side, we'll have 2 NOs, we'll have 1 Br2. The NOBr2s, since one's on the reactant side in step 2 and one's on the product side in step 1, those cancel out. And then the only product we have is 2 NOBr. And sure enough, we rewrite that, and that 2 NO plus Br2 equals 2 NOBr. That's the equation that we said was our overall reaction equation. So this tells us a couple things. It tells us here's our 2 step 1 and step 2 reactions. NOBr2 is an intermediate because we're forming it and then we're using it up. Okay, it doesn't show up in our final equation. And then if we add those steps together, we get our final equation, which is what we were told was the reaction equation before we started. So everything checked out on this. So in this case, we said that we have a rate limiting reaction step, which is number 2. So that's the one we're interested in. And we're told that the rate for that reaction was determined to be K2 times NOBr2 times NO concentration. So how do we find NOBr? So NOBr could react 2 ways. And so NOBr2 could react with NO to form NOBr, or it could be a decomposition reaction, okay? Remember that was that unimolecular reaction I talked about early on? In these types of situations, that decomposition reaction is not very likely. So kind of like with the termolecular thing, it's not the preferred thing typically. And so we're going to pick that first choice as we have before. For equilibrium, the rates forward and backwards are the same, those rates. We'll talk a little bit more about equilibrium. I think it's next chapter. I don't remember if it's next chapter, the chapter after. But for now, we're going to assume that. So here, if what we can do is we can do some substituting in here. So here we have the forward rate, here we have the reverse rate. And that's why there's the -1 on the K, that's the reverse. If we solve for NOBR2, so in other words, we just rearrange this by taking this K -1 and bring it over here. Then we can substitute that in, and we can substitute this into the formula, and we get these three rate constants, concentration of NO times concentration of BR2, concentration of NO. If we take all of these three rate constants and just say, okay, we're going to mush them all together and just say it's K, the different rate constant. Then we can rewrite this as rate equals K times, we have two of those NO, so it's NO times NO squared times BR2. So, and if we recall, that's the rate equation that they gave us at the very beginning when they were telling us about this. Okay, so there's something called a catalyst, we mentioned it there. And what a catalyst does is it's something that you put into the reaction system, and the idea is to lower that activation energy. So in this case, we have a reaction, and the red one, the red curve, is the uncatalyzed reaction, and then the black curve is the one with the catalyst. There's a couple things you should notice here. One is that the activation energy of the red one is higher than either of the activation energies in the black one. The other thing you'll notice is there's two things reacting, we have two activation energies. So that tells us in the black curve, so that tells us that we have an activation energy for whatever this first reaction is, intermediate is formed, and then the second one is second reaction occurred, activation energy there. So in this case, even though we have two activation energies for two steps in the reaction, the activation energy needed is less than the uncatalyzed one. When catalysts work, they typically work by changing what those intermediate reactions are. And so the end result is you get something, those steps require less energy. There's not as high that activation energy. But in general, that's the purpose there, is that you get that such that you lower the activation energy, make it a little easier for the reaction to occur. But it does that by usually changing the mechanism of what's going on. When we talk about catalysts, there's three main types. There's a homogeneous catalyst, there's a heterogeneous catalyst, and there's enzymes. So the homogeneous catalysts, those are ones that the catalyst is the same phase as whatever the reaction matrix is. So if it's a liquid solution, then it's a catalyst that will dissolve in the solvent. If it's a heterogeneous catalyst, then it means it doesn't dissolve in whatever it is you're doing. So once again, if it's a liquid solution that you're dealing with, the heterogeneous catalyst would be little pieces floating around in there. A lot of the heterogeneous catalysts are metal-based or carbon-based, things like that. And then finally, enzymes. Enzymes are typically what we were talking about when we were talking about catalysts in biological systems, and we'll talk about that a little bit too. Okay, as I said, homogeneous catalysts, they're in the same phase. Usually it's the catalyst dissolved in the solvent. Heterogeneous catalyst, so there's a couple versions of this. The example we have here in the slide has a solid catalyst bed with gas flowing over it. And this is a catalyst type that I bet all of you use, if not every day, close to every day. Any idea of an example of this type of catalytic process? So in your car, you have a catalytic converter, okay? And that's what cuts down on the pollution and things like that. That's what a catalytic converter is. It's a metal catalyst bed, and the exhaust flows over it, and that's how the reaction occurs. If you may have seen this in the news lately, but there's been an increase in thefts of catalytic converters off of cars. And that's because a lot of the catalytic converters have something called palladium in it. And palladium is a super expensive metal. So I'll give you the same disclaimer I gave the last class. I'm not advocating anyone steal catalytic converters or encouraging that. Please don't do that. But that's why it's suddenly become an issue. Palladium is much, much more expensive than gold, for instance. And so palladium is a really active metal in terms of catalytic properties. And so it's in those catalytic converters, there's a bed of palladium in there or some similar metal. And so the point is that that's an example of a heterogeneous catalyst. Another example would be if it was in solution. People like heterogeneous catalysts a lot of times because when you want to reuse the catalyst, you simply just filter it out. You can do a physical filtration and remove the catalyst. And that's a pretty easy thing to do. In a homogeneous catalyst, it might be a little more difficult to get the catalyst back if you want to reuse it. These heterogeneous catalysts tend to be used over and over and over. And if you want to repurpose heterogeneous catalysts, since they're often metal, you basically just heat them up to really high temperatures and burn everything off, and then they're good as new. Okay, we have a lot of biology types here at Webster, so let's talk about the biological catalyst, and that's where we're talking about enzymes. And so enzymes are usually pretty good sized molecules. And so they have regions where the reactants can attach to it. Okay, so just as with our other reactions, you got to have that contact. And that region that the reactants can attach is called the active site. And then the reactants are referred to as the substrates. So you hear people talk about substrates all the time in biology. That's the reactants. I don't know why they don't say reactants, but they don't. And so you have that active site on the enzyme, you have the reactants or substrates that have to match up. And the matchup has to be, there has to be a physical matching. And for years, people have described it as a lock and key model. So just as that key that you put into a lock has to have the exact right ridges and cuts in it in order to make the lock to unlock or lock, it's the same with this. So you have your enzyme, you have your substrate, and there's some physical orientation and physical structure that's needed. If the substrate doesn't fit perfectly into that enzyme, then nothing happens, okay? It can't react. But the idea is that you have this fit in and forms this enzyme substrate complex, and then because it fit in and it's the right orientation and everything, then the reaction can occur. And then you get whatever the products are. And so over here on the right, you see an example where you have some larger molecules and you see something fitting in with the yellow exactly in there, and then a reaction can occur, whatever that is. These enzymes tend to be very specific, and you can kind of see why. Kind of big things, you got some unique geometry that you have to fit in there, and then you can do the chemistry. So this is what you tend to see in the biological world, are these enzymes with this lock and key type of idea. Okay, any questions about the stuff we went over so far? All right, what I'd like to do is just finish up by here's some homework problems you can do. And I'd like to just go through a couple of them. So let me see, the first one is 1461. And what we're told in this one is that we have a first order reaction and we're told what the rate constant is. 2.75 times 10 to the minus 2 reciprocal seconds. So that means 1 over second. And we're told it's at 20 degrees. Then we're asked, what is the rate constant at 60 degrees C? Okay, so we're told what it is at 20. We want to know now what it is at 60, and we're given the activation energy. Okay, and so let's take a look at how we solve this problem then. You have our formula, the Arrhenius formula, for when we have two temperatures. Remember the one I told you we want to get good at. So that natural log of K1 over K2 equals activation energy over the gas constant times 1 over T2 minus 1 over T1. So remember that K1, because of the 1 subscript, goes with T1, and T2 goes with K2. Got to keep those straight in our minds. So we were told temperatures in degrees C, our rate constant is based on Kelvin. So we have to change those temperatures from degrees C to Kelvin. And so we went ahead and did that and got 333 for the higher temperature and 293 for the low. Remember, that's the 273 plus the degrees C. We were told our activation energy, except when we were told it, we were told in terms of kilojoules per mole. Well, our gas constant is in joules. So that's why this is 75.5 times 10 to the third. We had to convert that from kilojoules to joules. And an easy way to do that is to just take that kilojoule number and times it times 10 to the third. Remember, 1,000 joules equals 1 kilojoule. So now we do that. We've got our units right. We've got our temperature in Kelvin. We've got our activation energy in joules. So we've done that. We go ahead and plug in that rate constant that we were given. And now we just need to solve for, the other rate constant. Okay. Here's where we remember we're working in natural log of this. So what we're going to have to do is use that e to the x or a to the x or however your calculator has it, e to the x key to take the anti-log, because we're going to have to find the anti-log at some point. If we do all that correctly, then we should get 1.1 seconds to the minus 1 as our K2. So here's what I ask you to do, even before you start working on the homework problems. Simply take the numbers that I have here in this equation and see if you can use your calculator to get that 1.1 value. If you can't, you may have to look at your calculator menu, instruction book or something like that, or the menu on the little card they give you or something. But make sure you can do this calculation, because we're used to working in base 10 logs. This is now the natural log, and that means you're going to have to find the anti-log. You're going to have to use that e to the x key or whatever type of key your particular calculator has. Okay? Okay, part B of this is a similar problem, same idea, where we're using this Arrhenius equation for two temperatures again. That's that natural log K1 over K2 equals EA over R, and then times 1 over T2 minus 1 over T1. So we're given some a rate equation for the rate constant value for at the 20 degrees. We're given the activation energy, and we want to calculate out what K is at 60 degrees C. So once again, we need to change our temperatures into Kelvin from C, and we want to change our activation energy from kilojoules to joules. So now it's 125 times 10 to the third. We have our rate constant, those units, joules, mole, Kelvin. So that's why we have Kelvin in temperature and joules in activation energy. And then over here in the natural log side, we go ahead and put in that rate constant value that we were given for the 20 degree. So we said 20 degrees was T1, so that's why we have T1 here, 293, the second one, and we have that rate constant from the numerator on the natural log. Once again, if you go and do that math, the answer you should get is 13.1 seconds to the minus 1. So take some time practicing those problems, making sure you understand how to set them up, and make sure you understand how to use your calculator, okay? Okay, then the last one I want to go over is number 1469. And what we're given here is this kind of reaction, potential progress, potential energy plot, where on the x-axis is the progress of the reaction, so you can think of that as time. And then the y-axis is potential energy. And so we're starting with A as the reactant, and we're winding up with B being the products. So the first question we're asked is, how many intermediates are there in this reaction? Well, remember we said an intermediate is something that doesn't show up in the end, right? And we look here and we see from A to B, we see A, we see the energy going up, we reach the activation energy, and now we form B. Then B reacts, go to that activation energy, and now we have C. C reacts, and we go to D. So these two valleys that we see in this plot that are labeled B and C tells us that B and C are two intermediates that form. So stuff that formed, okay, it wasn't these things that we have at the top of the activation energy, which aren't stable. B and C are stable. One or two, we could probably isolate them. And so in this case, we had two intermediates form. How many transitions do we have? Well, we go from A to B, that's one transition. Then we went from B to C, that's another transition. And then we went from C to D, so that's another transition. So we had three transitions there. So if we were writing reactions out, we would have had, for a mechanism, we'd have had some reaction to explain going from A to B, some reaction to explain going from B to C, and then finally another reaction going from C to D. And then if we added all three of those up, it should be whatever that equation was from going to A to D that we would have had written in the beginning. The next question was, which of these takes the most time? It's kind of difficult to see on here. To me, they all actually kind of look similar because this reaction progress is kind of the time scale. So really, you're just looking to see the time from A to B, B to C, C to D. The official answer is C to D. To me, it's kind of hard to tell. I didn't get a ruler out or anything. But the point is that you're measuring the amount of time by looking at what it takes to go from, in this case, A to B, B to C, C to D. And whichever takes the longest, that would be the longest reaction time. And obviously, if it takes the longest time, that's the rate limiting step, right? And then finally, the other thing you can get from this is, if you know the potential energy you started at, and you know where you wound up with, so in this case, our delta E would be positive, because we started at a lower potential energy and wound up at a higher one. And so it would be positive. So from a plot like this is the kind of information that you can get. You can get, how many intermediates, how many steps in the reaction, what is that potential energy before and after, and get that kind of information. Okay, any questions about these homework problems that we just went through? Okay, if not, then that'll be it for today. Just a reminder again, Tuesday will be an exam on chapters 13 and 14. So on Tuesday, just go into Canvas during class time and please take the exam. And then I will see you guys next Thursday. All right, thank you.